All right, back at it again. Problem number 21. Let's consider this differential equation for x and y greater than 0. We're going to use a little Euler's method starting at the point 1, 2 with intervals of width 0.2 to find an approximate value when x is equal to 1.6. So I'm going to be looking for an approximate value of y of 1.6. And Euler's method is going to give me that. Okay. So let me break down the basic setup of how, at least in class, how we built this. And we're going to do 3 steps. I'm not pleased with that line. Let's do this. Well, that wasn't even any better. Let's do that again. Good enough. Okay, so we're going to do 3 steps. And those 3 steps are going to go from x equals 1, y equals 2, to x equals 1.2, y equals something I don't know, 1.4, something else I don't know, and then whatever my final value is, that's what I'll get for y of 1.6. So each of these processes, I don't know, I do math, are going to yield values for me in the end, okay? So what we're going to do is we're going to take dy dx times the width, right, plus our previous y, and that's going to give us our next y. Okay, you might remember that from class. If you don't, see the videos. This would be in chapter 9, differential equations, slope fields, all that good stuff. Okay, so I'm going to take dy dx, located at the point 1, 2. Okay, so dy dx, I'm going to use this for dy dx, located at 1, 2. Okay, so that'd be 2 over 1 plus the square root of 1 times 2, times h, which is 0.2, plus our previous or our current y value, which is 2. And when I use my calculator, this is clearly going to be a calculator allowed question. I get the following value. Okay, I'm excessively going above and beyond. And I'm going to keep that stored in my calculator, but just for the time being, I'm going to write this as a placeholder. But I will continue when I have to use calculations involving this y value. I'm going to use that. Okay, so this is just a placeholder right here. All right, so now our next dy dx is y, which is that ugly thing, placeholder yet again, but in my calculator I'm actually using the longer version of it. Now my new x value is 1.2 plus the square root of 1.2 plus that massive number, okay? And I'm not doing this exactly how you should. I'm just trying to show you the basics of it. Okay, I'm going to take that again times our width plus our previous y value, the, again, placeholder with all the extras involved in the actual calculation. That's going to give me an approximate value for y of 1.4 to be 2.319712,374. Okay, placeholder again, 2.319. I would never round until the very end, to the last value when you get to 3 sig figs. And then same process, 2.319 over 1.4 plus square root of 1.4 plus 2.319 times 0.2 plus 2.319, all of that stuff. That's going to give me y of 1.6. Okay, and that value comes out to be, to 3 sig figs, comes out to be 2.46. Therefore, y of 1.6 is approximately 2.46. I should do some lasagnas here. Or I could, in this notation, write 1.6 comma 2.46. All right, there you have it, Euler's. I'm thankful that we didn't have to go more than 3 intervals on that one. That would have gotten very ugly quickly. Actually, it did after the first value. But that would be how to use Euler's in order to find an approximate y value. Okay, part B, it says consider the same differential equation. Use the substitution y equals ux to show that x du dx is equal to u over 1 plus root u minus u. Now that might be a v, and my whole life here as a IB teacher I've been just using the wrong variable, but it doesn't really matter. Okay, you can probably see that we're going to end up using the homogeneous method. So here we go. Let's do this. Okay, so if y equals ux, then u equals y over x. Okay, which is something that we're going to use here possibly later. But then if I use this and I do product rule, dy dx is equal to du dx times x plus u. Okay, product rule there. What we're going to end up doing here is I'm going to divide, looks like I'll divide both sides. Never mind, lost my train of thought there. So what I'm going to do is I'm going to take dy dx and I'm going to replace it with this expression here, right? So now I'll have it in terms of u, and we can do some manipulation on it, okay? And I'll use this y equals ux in just a moment as well. Okay, so if dy dx equals du dx times x plus u, and that's equal to this, okay, y is equal to ux. So I'm going to replace this y with ux. I'm going to replace, actually I'm not going to replace the x, but I am going to replace this y also with ux. So the expression under the square root there will be ux times x, which is ux squared. Okay, now what I'll get here is I'm going to subtract this u right here, to the other side, and I'm also going to take the square root of x squared and bring it out as an x. So I will have du dx times x, subtracting u over, you'll see in just a second. This will be x plus x times the square root of u minus u. Okay. I am going to then, let's do this. I see something that I like. Du dx times x. I'm going to factor an x out in the denominator, and I'm going to reduce it with the x in the numerator. Okay, so if I were to factor out an x in the denominator, I'd have 1 plus root u. I'm leaving this u out here for just a moment. And then I'm going to reduce out the x. So du dx, okay, du dx times x is equal to u over 1 plus root u minus u. And I believe that's where we wanted to be. Yeah, there it is. Okay, cool. That was 3 marks. Let's see what they've got in store for us in part C. Okay, a 9-mark question. Hence, find the solution of the differential equation in the form f of x y is equal to 0, given that y is equal to 2 when x is equal to 1. We're going to find the value of y when x equals 1.6 in a different way. Okay, so we already did that using Euler's. So let's take what we know for part 1, which is x times du dx is equal to u over 1 plus root u minus u. And I'm going to get a common denominator and bring this u in so that I can make one expression, one term. So I'm going to multiply bottom and top by 1 plus root u. Okay, so let's clean it up just a tad. So that'd be u minus u plus u to the 3 halves, all over 1 plus root u. Okay, we now have this in a separable form. I'm going to clean the top up here on the right side. This u will cancel with that u and make this a negative. So what I'll technically have here is just minus or negative u to the 3/2. Okay, I know that isn't the prettiest, but that's what I've got. Okay, so now that we've got that, this is in a separable form. Therefore, I'm going to separate the variables. And how I would do that is I would have 1 plus root u over negative u to the 3/2, just multiplying by its reciprocal. And then I'd have 1 over x dx. Okay, now I've got it in a separable form, and I'm hoping I can integrate relatively easily. I can see already what I'm going to have on the right side. I'm going to have ln of x. On the left side, this isn't actually as bad as I think you might make it out to be. But what I'll have is, if I split this into two separate integrals, or two separate terms, I would have negative u to the negative 3/2, right? That's 1 over negative u to the 3/2 minus, what would that be, 1 over u du. So if I integrate that, I'll get positive 2u to the negative 1/2 minus ln of u. Okay, and then on the right side I had ln of x plus c. Okay, ln of x, ooh, that was kind of sloppy, plus c. Okay, cool. So let's think about what we've got here in terms of y and x. Okay, this is u to the negative 1/2, so that's really 2 over u to the 1/2. So it's not square root of y over x, it's actually 2 square root of x over y. Okay, and then I have minus ln of u, which is y over x, is equal to ln of x plus c. And I believe the condition they gave us was 1, 2. 1, 2. Okay, so if I have 1, 2, that gives me 2 root 1 over root 2, so that'd be root 2. Okay, that's 1 over root 2, minus ln of 2 is equal to ln of 1 plus c. All right, so it looks like c equals, I'm going to simplify this. If I rationalize that, I get root 2. So I should have root 2 minus ln of 2. Okay, I like that. That's pretty good. Okay, so now I'm going to go back to this, and I'm going to input c in there. Okay, so I have 2 over, I have 2 root x over y minus ln of y over x is equal to ln of x plus root 2 minus ln of 2. Okay, a little bit of work, but I want to set this in a form where it's equal to 0. Okay, so that would be 2 root x over y minus ln y over x minus ln of x plus root 2, might run out of room here, oops, I'm sorry, minus root 2 plus ln of 2. Okay. I'm thinking what they want is potentially for this to be as compressed as possible. Let's see what I could do. I think what I could do if this might be going too far, but I could have 2 root x over y minus root 2. So I've taken care of this term and this term. And I could take these 3 logs, right? And I could put them all together, potentially. Let's see what we got here. This would be minus ln. Okay, so if I take y over x, ln of y over x minus ln of x, that's going to be ln of y over x squared plus ln of 2. That's going to be times 2. So that would be pretty clean. That's not that bad. Okay. So there you go. I would say IB would probably accept either of those. Okay, either of those 2 forms. And they haven't really designated which one they want. They just want it in terms of x and y and equal to 0. So I think we're good there. Okay, part 2. Let's look at what that's asking. That said, find the value of y when x equals 1.6. Okay, so really all I would do here is I would plug in a 1.6 for x. And I would use our calculator here. And I would solve. So this is pretty complex, but I mean, honestly, with your calculator, I would just go ahead and evaluate in this way. I think using the calculator, I got 2.45. So thinking back, I think our Euler's, gave 2.46. So Euler's was relatively, it was relatively accurate. I'm guessing because of how small the intervals were and how few there were. Well, no, if there were more intervals, it'd be better, but it looks like it comes out to be pretty clean. So there you go, guys. That's it for problem number 21. We'll see you in the next video.